most Windows applications have within them hidden a 1980s DOS application. That application is hidden in there, never really gets to run anymore. Not sure if you've ever seen that. Maybe some of you have, maybe some of you haven't. In this video, we're gonna look at the hidden DOS application, the hidden 1980s DOS application that's in most Windows programs, but you never see it. Of course, I'm talking about the MS-DOS stub that we talked about in the prior video when we covered the PE executable. In this video, we're gonna shatter the mystery and look at that program and get in there and have Ghidra show us a disassembly of this small little program that's in there. This is meant to be a fun video, but it's also meant just for people who've never seen that stub, and it's always kind of this thing they gloss over, to just have a quick video, show it to you. Let's look at it. Let's see what it's all about. Get it something that's out of the way, not such a mystery. Okay, so I'm going to search for Visual Studio. We're going to click to download Visual Studio, download Community Edition. If you have Professional or Enterprise installed, that's fine. We're going to go here to install this. Click Continue. Okay, terrific. Now I'm going to choose the desktop C++ environment. That's the one that you want. And then just click Install. Skip this for now. Dark. And we're going to go Visual C++. Okay, great. Visual Studio is installed. I'm actually just going to exit. Going to exit here. Going to exit here. Okay, so the next thing I want to install is VS Code. I'm going to download this, and we're going to run this. And I'm going to accept this there. Okay, we're going to say install. So after Visual Studio Code is installed, started up, we're going to go to the marketplace. Type in hex, H-E-X, in the marketplace. There'll be a result, hopefully near the top, that's a hex editor from Microsoft. So click Install. And after that's installed, you can just close and then close VS Code. All right, let's get into it. We're going to use the same sample console application, not because we have to, but just for sake of uniformity. If you want to follow along, I recommend you use that. The GitHub link will be down in the description. So remember, in the last video, we searched for image DOS header, and we did so by doing Control-Shift-F to find in files, and we selected Visual C++ include directories, and then we did find all. And when we did that find all, it actually found it here in the winNth file right here, which I already had up. And you can see that that header is here. And in that last video, we looked at the MZ header that goes in here, and we also looked at this C paragraph, which is count of paragraphs in the header. And we also looked at this LFA new, which is an offset to the new header, the PE header. But what we didn't stop to look at is the DOS program that is hidden in this initial part of the code. So what we're going to do is we're going to have debug selected with x64 in the console app, and then we're going to do build and build solution, or you can do rebuild all, just to make sure you have a good debug version of the console app built. And with that done, I'm going to go to Tools, I'm going to go to Command Line, PowerShell, Developer PowerShell, and that's going to go into the root of the project. I'm going to go into x64, debug, and here is the console application. I'm going to type in VS Code to go into that console application. This is what we did in the prior video. And you can see we have our MZ header here. And then here is the 4 for 4 paragraphs of the size of the header. So that would be 1, 2, 3, 4 rows. That's that C pair header. Here at the end of that 4 paragraphs is the F8, which is that LFA new, that offset to the new header. And if we go to F8 by going to line FO and then going to column 8, you can see that takes us to PE00, which is the PE signature. Okay, great. Let's start up Ghidra. Now I have Ghidra here started up, and I'm going to make a new project, and it's going to be non-shared, and I am going to call this, DOS stub tutorial, and I'm going to click finish. And then what I want to do is I want to go to simple message box. I want to right click and choose open folder in File Explorer. When that opens up, it opens to the root of the project. Let's go into x64. Let's go to debug. This is the exe for our console app. I'm going to bring this down here. Going to lower this window a little bit here just so we don't take up so much real estate. Going to go back over to Ghidra. Now I'm going to drag the simple message box app into Ghidra. We're going to leave the defaults initially. We're going to come back and change something here. I'm going to click OK. I'm going to double click. I'm going to say yes. I'm going to say analyze. I'm going to click OK. Now I'm going to look for the scroll bar here in the side, and I'm going to bring that way up to the top. We can see way up at the top is the MZ header, and we can see here are those structure fields just like the ones that we were looking at in image DOS header over here. So here's image DOS header, here's magic, and here's CPAR header. So you can see here in Ghidra, here's CPAR header, there's the 4, right? If we go to the end of this section here where LFA new is, you can see here's F8. And if you look right after this F8, you can kind of see here at the 40 offset, you can see that there's a little DB here with some bytes, and it says actual DOS program. But you notice because this is a 16-bit DOS program, it has not been disassembled by Ghidra. So what we're going to do is we're going to exit this. We're going to choose to save. Doesn't really matter here yet. I'm going to right click. I'm going to choose delete. I'm going to go back to our Explorer window and redrag simple message box back up here. But before I click OK, I'm going to bring the drop down here and I'm going to choose old style DOS executable MZ. I'm going to click OK. I'm going to click OK. I'm going to double click to load up. Going to click yes, going to click analyze. And you'll notice here that this is a 16-bit disassembly. And you can see that this is the program. In fact, if we go back to our VS Code raw hex dump, you can look here and see that there's 0E, 1F, BA, 0E, and so forth. And you can see that that happens after the end of that header where the LFA new F8 is. So the DOS program begins here at 40. You can actually see a string that the DOS program uses. Here's that string. I'm sure you probably saw this before. This program cannot be run in DOS mode. And you see this 0E, 1F, BA, 0E, like that. If I go back over to Ghidra, you can see 0E, 1F, BA, 0E, and so forth. Except Ghidra is making a lot more sense out of it by showing us the machine instructions here and the disassembly. So let's break this down really quickly. What's happening? Well, the code segment is being pushed on the stack. Then that value of the code segment, which is now pushed on the stack, is being popped off the stack into the DS register. This was common back in the DOS days to see this kind of thing. This is essentially the start of the program. The start of the program essentially receives the code segment already set. It wouldn't be uncommon for a program to want to, at least initially, set its data segment equal to its code segment that it gets from DOS when DOS hands off to the program. So DOS hands off to the program, CS is already set. The program pushes CS on the stack, or the value of CS on the stack. The program pops the value of CS off the stack and into the DS register. And that's the initial setup. So keep in mind, DOS programs had to manage segments like this, something you generally don't see in user mode programs today when you're working in a user mode program and you're debugging and whatnot. You generally accept that all the segments are set up properly. That's because it's a very large, flat, and spacious model, and there's usually plenty of room there to do things within that address space that you're given. Back in the DOS days, programs might manage their segments if they had to take advantage of different areas of memory that couldn't fit into a single segment with everything all together. Now, if you look here, you see the DX registers being loaded with E, the AX registers being loaded with 9, and then there's an int21 call. Well, int21 or interrupt21 was the hook into DOS APIs. You would put the API code for DOS into the AH register. In this case, that's 9, which means print a string or print the string of characters until a $sign is encountered. We go over here to VS Code and we can see that there's a $sign at the end of the string right here. We don't see it here yet. We'll get to that in a second. This DX is the offset to the string that we want DOS to print. Actually, the full address of the string that we want DOS to print is in the DS:DX location. That's the data segment register DS:, and the offset supplied in the DX register. The offset in this case is E, or 14 in decimal, but we don't care about decimal right now. E is fine for us. That offset of E is actually located right here, down here at E. We'll get to that in a second. So essentially what this is doing is it's loading the offset to the string that we want to print in the DX register. It's loading the code 9 into the AH register, which is the code for DOS to print a string until it encounters a $sign. It then issues a software interrupt 21. That's effectively like calling DOS via the int21 vector. That was very common to do in those days. There might be APIs or interfaces that you could get to via interrupts of one kind or another. But int21 was particularly well known. int10 was, I believe, the video or VGA interrupt, and that had a whole lot of APIs, similar to the way DOS did as well. When DOS is finished printing the string, it will issue an IRET, I-R-E-T instruction, which will cause it to return here right after this int21 instruction. That means when DOS does the IRET after printing the string, it will return to this 0009 offset within the program. You then notice the program loads AX with 4C01. Well, what it's effectively doing in one step is it's loading AH with 4C, which is the API for DOS to terminate the program. The AL register is going to get 01 here, which is the actual exit code for the process. So this is going to be an int21 here. So a 4C01 in AX and an int21 is going to call into DOS. It's going to tell DOS to terminate the program. That's the AH equals 4C. That's terminate program. And DOS is going to use the value in the AL register, that lower 16 bits, as the exit code for the process. See that kind of similarity to what we even see today in user mode programs? Well, there's a lot of elaborate stuff that goes on, especially around security stuff and the stacks and whatnot. Some of those fundamentals are kind of unchanged in some rough sense. And after this terminate program, the program's ended. It's over. So the size of the program is pretty much these machine instructions plus the length of the string. Now, speaking of the string, where is that string? We see a push instruction at E. Why don't we see a string here? Well, the reason why is Ghidra disassembled this thinking that it was code. But we can help it by right-clicking. We can start with just the first character. I'm going to do a clear code bytes here. And you can see it puts a question mark here, and we see the letter T. Let's actually keep the cursor blinking here on E and grab the scroll bar and go to the end here of this block of data and right-click, and I'm going to do clear code bytes. And then I'm going to grab the scroll bar and go way back up to the top where we were, and you can kind of see that the string is a little more clear now, even though each character is taking up a line. Before we fix that, though, what I want to show you is that at the end here, you can see the $sign, which terminates the string, but you can also see that that $sign is followed by a 0. And we can use that to our advantage in Ghidra. I'm going to scroll back up here to E. I'm going to right click on E, and I'm going to choose data, and I'm going to choose terminated C string. Even though this is a string that's terminated with $sign, it happens to have a 0 after the $sign. So treating it like a terminated C string is going to make it look nice in the disassembly right away right now. So here we go. And there we go. There's our string. And so here's the program. This is the DOS stub you're looking at. This is the hidden DOS program that most Windows programs, if not all, have in the beginning stub there. The stub generally doesn't run unless you're running the program in DOS. Let's actually do that. I have a DOS emulator set up, so I'm going to actually maximize this so the taskbar is visible. Here is the DOS emulator. It's DOSBox, and you can get that at www.dosbox.com. If I run this command, so let me just show you, there's nothing visible here on C. If I type in mount C, C:\asm source DOS, we look at C, and we can see there's debug.exe there. Now, we'll get back to that in a second. That's actually the old DOS debug.exe that I was mentioning in that WinDBG video a couple weeks ago. So what I want to do is go to that asm source DOS mount point. So let's go over to that. Here's the mount point right here, and you can see here's that same debug.exe. So in this window, I'm actually going to do a copy of the simple message box.exe, the debug x64 version. And so I'm going to copy that to the local directory. So you can see it's copied right here side by side with debug.exe. And I'm also going to copy C:\Windows system32 notepad.exe. And so now we have two Windows applications copied into that mount point. Let's go back over to the DOSBox. And if we go into the C drive of the DOSBox, I have to actually refresh. You have to hit Control-4 to get that refreshed with the current contents. Okay, let's see if those other programs are here. So now we can see there's debug.exe. That was there before. Here's notepad.exe, and here is simple-1.exe. Now you might say, what's the -1 for? Well, remember, DOS doesn't support long file names. And what they did is when they migrated from DOS to an operating system like Windows 95 or Windows NT, which supported long file names, on those OSs at the time, and the feature still exists today, there's a support in Windows to support dual file names, an 8.3 file name for a file that may have a long name. So simple messagebox.exe has both a long name, simple messagebox.exe, and a short name that is simple-1.exe. This allowed long file name files to be used from environments, DOS environments that might be connected via network, or you might be sharing disks with somebody or things like that. It allowed the 8.3 environments to coexist with the long file name environments. Now, if we go and run simple-1.exe, we can see it says this program cannot run in DOS mode. Now, you might think that's a message from the shell, but it isn't. That's actually the program that we were just disassembling. Now, if that stub were not there, some machine instructions that are meant for running in the Windows environment might run in the DOS environment and cause it to lock up or some strange thing to go on. So the stub was a friendly way of supplying information about what was going on and then exiting, politely. And it's just telling the user that they can't run this in DOS mode. Okay, so now let's try Notepad, and it has the same message. Now let's go quickly over to the simple message box command line here, where we're in the folder where the debug version is, and let's actually go and just run the exe. So you can see the same binary will actually function here and display the message box. But if I go back over here to the DOSBox, we can see that when you run this here, DOS knows nothing about UI. DOS knows nothing about a PE executable. DOS knows nothing about how to display a message box. All it knows is it runs that stub and exits, right? So when you run that, the stub runs. Okay, let's run that in the debugger. So we're going to run the old DOS debugger. We're going to say simple-1.exe. And right when you start this up, we can do R to look at the registers. And we can see that there's a push instruction, and we can see that the code segment is set up with 76A. Let's actually do a U instruction. The U instruction is going to unassemble, and it's going to unassemble from this last location that we unassembled from, which is no location, so it just does it from here. If I run unassemble again, it's just like WinDBG. It will continue on. They're not identical though. WinDBG is much more advanced. You can navigate around much more easily there. Here, what I would do to go back to the top is I would say, well, let's look at the registers, and we see that the code segment is 76A. And we see that our instruction pointer here is 0, so I'm going to put 0, and that'll give us an unassemble back to where we were. So you can see here there's a push CS, a pop DS, that assigns the code segment to the data segment. Now they're equal. So any offset into the code segment will access the same byte as any offset into the data segment. This was not uncommon for a DOS program to perform, at least initially, if not for the entire lifetime of the program. And then we see it loading in the E to DX and all the other stuff that we looked at right here. Now, what we can do is do R to see what the next instruction is and all the current register values. And we can use the T instruction to trace over that push instruction. And watch the DS register after this pop instruction. I'm going to do T again, and you can see DS changes to 76A. Now DX is going to load with E. Notice that DX has 0 before that instruction. I'm going to hit T, and you can see DX gets E. Do you see the similarity with this decades old, very primitive debugger compared to the debugging tools for Windows that we have today? The current debuggers are far more advanced and have so much more stuff going on that you can use. But you can kind of see where that backward compatibility was honored along the way. And it has this consistency over many generations. So you can see here that the DX register got the E value. Now notice the AX register has FF. That is the AH register, which is the high byte, has an FF, and the AL register has FF. So they both have FF. Now the next instruction is going to move 9 into AH. Let's hit T to see what happens. We can see the high byte of the AX register was set to 9, as would be expected. And then we see an int21. Now, if I trace into this, it's going to trace into the DOS API call. And that could be a very long endeavor, tracing manually through that entire call. What if I want to do what today we call step over, where I want to run to the return point? Well, let's use the U command to do unassemble. And you can see here's the int instruction that we want to skip over. We want to skip over that instruction and stop at the 9 instruction, the instruction that is at offset 9. We could manually set a breakpoint there, but if we hit question mark for help, we can look here at the go command and we can see that go command takes addresses. When you specify address after the go command, it's like you're telling the debugger, set a breakpoint for me at this address and remove the breakpoint the next time you stop. The next time you stop might be when you hit this breakpoint, or it may be when you hit some other breakpoint, or some other debugger event causes the debugger to break or stop in some way. That's no different here. So if we go back and do R and then do U at our current code segment, which is 7.6a, and then our current IP is 7, we can see that this instruction at offset 7 is the one that we're currently at. That's the interrupt 21 we want to skip over. We can type in G and space and then type in 7.6a:9. And when I hit enter, the debugger is going to first set a breakpoint at offset 9. It's then going to let the processor run full speed. And the next time the debugger stops, it's going to remove the breakpoint that it sets for us when we run this command. Now, the debugger may break at some other location or at our breakpoint, but the key point is the address you specify on the G command in the way I'm specifying it here is going to temporarily create a breakpoint for us and then remove it when the debugger stops. WinDBG today and the various debugger tools, the debugger engine I should say, has the same capability if you go and look at the help text for the go instruction. So what we're expecting to see when we hit enter is that the string will be output to the console and that our breakpoint will be hit. Let's see what happens. And there we go. You can see here's the string gets output to the console. That's what the user would see if they were running accidentally a Windows program while they were in a DOS environment. And we can see the next instruction is this move AX, 4C01. Now, move AX 4C01, that's going to move 4C into the AH register. That is the API call to tell DOS to terminate the program. And the 01, which goes into AL, is the exit code for this process. After it's terminated, it will return that exit code. So I'm going to press the U command so we can see all these instructions. Here's the setup. Here's the interrupt call. This interrupt call will not return. DOS will terminate the program and return to whomever ran this program. Typically, it would return to the shell for the user to enter the next command or some such. In this case, since we're running under the debugger, DOS returns to the debugger, since that's the entity that started the program. So let's hit G to see what happens. We hit G and DOS terminates the program that we're running under the debugger. Then DOS returns to whomever started that program, and that would be the debugger itself. The debugger detects that return and says, hey, the program terminated normally. If you run a console program in WinDBG to the end, you'll see kind of similar behavior. Of course, it's changed because it's a very different environment and whatnot, but there's a similarity there. And when you deal with that similarity over many years and you have that effort for consistency, it really makes the debugging experience nice to deal with from generation to generation. All right, everybody, that's it for this video. Hopefully DOS header demystified and a little bit of history added in there. If you enjoyed this video, I hope you'll click like. It really does help. And if you want to subscribe, totally sensational. That would be awesome. So subscribe if you want to. It really does help the channel. Other than that, just be well, be safe, rock it out, make it happen. All right, until the next video, be well. All right, everybody, take care. Thanks. Bye-bye.